statement. Maybe I was wrong in that interpretation. Maybe you're just shouting at me because you didn't think it was obvious. Our limiting reactant concept. We take a look at making a cheese sandwich. 1 cheese plus 2 slices of bread gets us 1 sandwich. We have 5 slices of cheese, 8 slices of bread. How many sandwiches can we make? And people are able to come up with this calculation in their head, straightforward, right out of the gate. Stop doing it in your head. Write it down. You need the formal notation to go through and solve. 5 slices of cheese, and I need to make sandwiches. How do I convert cheese into sandwiches? One sandwich is 1 slice of cheese. Comes straight out of my balanced chemical equation. Okay, or in this case, my balanced sandwich equation. Okay, and I end up with 5 sandwiches. I heard a bunch of people shout out 4. This says 5. Okay. Why is it not 4? We didn't take into account how much of the bread was present. In this calculation, what did we assume about the bread? There's enough. Okay? There's an excess of bread. That's how we get 5 sandwiches. Okay, so now what we'll do is assume the other situation. We have enough cheese. How much sandwich can we make out of our bread? So we would take our 8 breads. We again want to convert into sandwiches. How do we do our conversion? Well, bread, sandwiches. What's our conversion factor? 2 bread, 1 sandwich, and we get 4 sandwiches. Okay. You did this calculation. This is the same thing you're doing with every single chemical reaction. Okay. The thing that you have to watch out for is the units associated with this. When we go through to do this calculation, does that say anything about the grams of bread? No. What are we saying about the bread? There's 8 pieces of bread. When we look at a chemical reaction, what we're converting between are the pieces, or the number of a species, not the mass of them. If we change this question to say 5 grams of cheese and 20 grams of bread, can we solve it now? Okay, well, how much does a bread weigh? We need that conversion factor. We need the conversion factor between mass and the number of particles, or the number of bread slices. Okay? Without that conversion factor, you couldn't solve the question. Same thing is coming back to our chemical reactions. Okay, come on. Oh, did I actually remove the example question? Yeah, I did. So, tough. Okay. The next concept we addressed was percent yield, okay, which is just actual over theoretical. So when we go into a lab to perform an experiment, we want to decide how good of a job we did. You run an experiment and produce 5 grams. I run an experiment and produce 50 grams. Who did the experiment better? You made 5, I made 50. Who did it better?
Depends on what you were trying to do.
Depends on what we could have made. For your 5 grams of product, you could have theoretically made 6 grams at most. Okay. Well, let's make it easier. Let's say 10 grams. So you were 50% successful. You should have made 10 and you only made 5. 50%. 50% in a class, that's pretty much failing. Sorry, guys. Okay. I should have made 500 grams. And I only made 50. What's my success rate? 10%. Who did it better? You did it better at producing 50%. I did it much worse at only producing 10%. So what we have to evaluate is not the raw number, but the percentage. How much was possible for us to go through and run the reaction? That is our theoretical yield. The theoretical yield will always be calculated. It's not something just given to you typically. It's something that you have to calculate. That said, to go through and calculate a percent yield question, say like this one, where you have to calculate it, that takes a lot of work. Okay? And I gave you 5 minutes to attempt to solve that one last Tuesday. How many people solved it last Tuesday? Yeah, that's kind of what I thought. Because it takes a lot of time. Okay? So how can we change the question to simplify it so now I can ask a percent yield question without having to go through and do a whole bunch of calculations? I can tell you what the theoretical yield is. Okay? If I call it theoretical yield, that's what I should be calling it. Okay? Your textbook doesn't quite follow that line, and so we come up with different names for what the theoretical yield is. Okay? The theoretical yield, because it is always calculated, is sometimes referred to as the calculated yield. Okay? So if we looked at the second to last question on the exam, I think that's right. Since you all have the exam. Nope, that was a lie. Third to last question on the exam. Yep. We're given a whole bunch of numbers. We're given 1.550 grams starting I'm given 0.617 grams oxygen released, and I'm told the calculated oxygen is supposed to be 0.607 grams. Three numbers. Okay. Which of those three numbers do we need to use?
The last 0.617.
Okay. When we calculate our percent yield, the unit must be the same for both the actual and the theoretical. Well, the theoretical is how much was produced. Well, I'm telling you right now, calculated O2. Okay. As soon as you see that word calculated, you can now drop that in at the bottom of our equation because that's where it belongs. What needs to show up on top? Okay. The actual. Actual what?
Actual yield.
Actual yield of what?
Oxygen gas.
Of oxygen gas. Why oxygen gas? That's the unit of my calculated yield. Where do I have units of oxygen gas?
Theoretical.
Somehow I think I swapped these numbers. Maybe I didn't. Let's read that question. Student releases. No, I did get it right. All right. We now have our proper formula. We can go through and calculate it. And what do we get for a number?
102%.
Okay, we would get technically 0.102. Okay. But when we're looking at a percent yield, we're always looking out of 100%. So we can multiply by 100. And we end up with a final answer of 102%. Make sense? Anybody have an issue with getting 102% yield? That's more than we started with. There's no way in hell that should have happened. Okay? What does that mean? You did something wrong. Good point. So what you should immediately pause and do is say, did I do the calculation right? Okay.
It's actually 1.02, not 0.102.
It's actually what?
1.02.
Oh, yeah, sorry. I can't do math. You're right, sorry. 1.02 times 100 gets us our 102%. Okay, either way, we're still at 102%. So we found a mistake, calculated wrong, still got the same answer though. Right. Did I put the proper numbers in there? Yeah, everything's set up. So what does that mean about the 102%? You screwed up the experiment. Calculation is fine. The experiment is wrong. Okay. Why ask this question? Because 9 times out of 10, you go through and get 102%, and you go, well, I can't have more than 100%. I'm going to do a different calculation. You can't just change the numbers because you don't like the numbers. Okay. If your result says you get 102%, you have to make sure your calculation's correct. The calculation is correct, which means you get 102%. That's what your experiment gave you. Okay? Now the question becomes, should it have given you 102%? No. You can now go back and analyze the experiment itself. Calculation is still valid. Your answer still comes out at 102%. Okay? Why does this show up? Because as soon as you get that 102%, 9 times out of 10, students just say, well, I'm going to change the numbers so that I get a number less than 100%. Okay? Meaning, you went through and said, I'm going to make up an answer and I'm going to hope that's right. Okay? Because it shouldn't be over 100%. It can be anything. It is the most common way to test percent yield. Have students get a value above 100%. Because then they instantly second guess what they know to be true, and they change the calculation around, okay, to get the wrong answer. Okay? Yeah, shake your head all you want. That's the way it's tested on. I can't hint anymore. Okay? So you got to watch out for that. Make sure you understand how to calculate your percent yields. Why is the other number included in there? Really to screw with you. Okay? If we only gave the last two numbers, the 0.617 and the 0.607, there are only 2 multiple choice answers. Okay? That's a lot of nonsense goat answers for the last 3. Okay? We need something else in there. So we throw in another number, which then means the possible permutations of multiplication and division, okay, goes up, and there's now a whole bunch of other places where you could screw up your calculation. Okay? That's the only reason that third number is provided. Okay? Make sense? Questions about that? Okay. So, percent yield. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. And only 0.5 moles of sodium hydrogen carbonate are produced. Then what is the percent yield of sodium hydrogen carbonate? So the first useful thing to write down would be percent yield equals officially times 100%. So I have to remember we'll include it. Are we given the actual or the theoretical explicitly in the question? We're given the actual. So actual equals 0.5 moles of our sodium hydrogen carbonate. Okay. So what do we need to do?
Calculate for your theoretical.
I need to know what the theoretical is. Okay. How do I determine the theoretical?
Divided by 100.
No. What units do I need on the theoretical? Moles, sodium hydrogen carbonate. So we could start it off with moles, NaHCO3. What am I starting with in my calculation? Okay. I'm starting with 2 moles of sodium carbonate. Okay. Yes, we also have the moles of water and the moles of carbon dioxide. But when you calculated how much sandwiches you could make, did we add up the bread and the cheese? No, we just focused on one of our materials. So here's one of our materials. How much sodium hydrogen carbonate can I make? What is the relationship between those two terms?
Is it two moles over 1 mole?
How do we figure out that relationship?
Looking at what the equation gave you.
You go back to the balanced equation. So number 1, I said balanced equation. Is the equation balanced?
Yeah.
I was hoping it was balanced. Yeah, it is. There's 2 on the left, CO2. Yeah. So this one's tricky because you got a lot of things that you have to go through and process and balance. So our equation is balanced. What number shows up in front of sodium hydrogen carbonate?
2.
Where's the 2? Sodium hydrogen carbonate.
The far.
The far right. We have a 2 in front of it. What number shows up in front of sodium carbonate?
1.
1. We run the calculation, what do we get? 4 moles of sodium hydrogen carbonate could be produced. Is that my theoretical yield? Why are you saying no right out of the gate?
Oh, never mind. You don't know your
That is moles of sodium hydrogen carbonate. Isn't that what I was looking for? We had 4 or 5 slices of cheese and 8 slices of bread. How many sandwiches could we make? Only make 4. If I had 5 slices of cheese, why can't I make 5 bread sandwiches? You have to evaluate the other starting materials and see how they convert through. Okay. So you got 2 more starting materials to check. Check them. Here's that conversion factor of 2 moles of sodium hydrogen carbonate to 1 mole of sodium carbonate coming from the balanced equation. There's the coefficients from the balanced equation. To solve this question, you must have the balanced equation because that gives you the numbers to put in front here. Okay, that's where those numbers come from, the balanced equation. That's what the conversion factor gives you. The numbers given in the question are values. They are not conversion factors. They are a value. Okay? I cannot drop that into that expression. Okay? So when you go through and look at this question, you have 3 theoretical yields to calculate. You have 1 for the 2 moles of sodium carbonate, you have 1 for 2 moles of water, and you have 1 for the 1 mole of carbon dioxide. You should have all 3 of those calculations staring at you right now. Okay? And numbers for each of them. If we go through and assume or look at each of those, if we started with the 1 mole of CO2, moles of CO2 needs to show up on the bottom. What needs to show up on top? And this will then get us our moles of our sodium hydrogen carbonate, which is what we wanted. What numbers need to show up in that conversion factor? Okay, 2 over 1 coming from the balanced equation. Okay, and we would end up for an answer of 2 moles of sodium hydrogen carbonate. If we went through and tested this with our water, our 2 moles of water, we want our moles of water to be in the denominator so the unit cancels. We want moles of sodium hydrogen carbonate on top. This will then give us our units of moles of sodium hydrogen carbonate. What numbers need to show up in front of those?
2 moles sodium hydrogen carbonate over 1 mole H2O.
2 over 1. Okay. Common mistake that happened, I won't name names, but you know who you are. You might end up putting a 2 in here. Okay, why are you putting a 2 there?
Because the 2 moles of H2O.
It means something different. The 2 moles of H2O that you were given is not a conversion factor, that's a measured value. As soon as we move into our division system, our conversion factor, we now have to evaluate a different meaning for those numbers. Those numbers come exclusively from the balanced equation. If we look at the balanced equation, the number that shows up in front of moles of water is 1. That's why it's a 1 and not a 2. Okay? Same thing goes back to our formulas. What the different meaning of each of our subscript numerals mean. Okay? You have to make sure that you track and understand what they mean, not just that there's a number there. Okay? Simple mistake, watch out for it. Particularly in a situation like this, where we're trying to make the question easy and have you not do a whole bunch of other calculations. Okay? That calculation would get us out to 4 moles of sodium hydrogen carbonate. So we are now comparing 3 numerals, or 3 values. 2 moles of sodium hydrogen carbonate, 4 moles of sodium hydrocarbonate, and 4 moles of sodium hydrogen carbonate. Which one produced the most amount of product that I could get in this reaction? 2 moles. Why not the 4?
Because CO2 is a limiting reactant.
CO2 is the limiting reactant in this case. I can only get up to 2. Once I achieve 2 moles of sodium hydrogen carbonate, how much CO2 do I have left? None. If I don't have any more CO2, can I continue the reaction? No. So your limiting reactant is the one that produces the smallest amount of product. Okay? That is now our theoretical yield. Okay? So our theoretical yield comes out to be our 2 moles. To calculate, what do we need to do? Was it H? Plug it in. Our actual yield was what? 0.5. Our theoretical yield was 2 times 100 gets me 25% yield. There's my answer. This is a much more advanced question because you have to do multiple calculations within it. Okay. The level of difficulty you can expect on the final, okay, because everybody loves this example, our cheese and bread sandwich. That is really kind of the level of difficulty you're looking at. The one thing that scales it a little bit further, it's no longer cheese and bread, hydrogen gas and oxygen gas to produce water. So we end up turning it into a chemical equation as opposed to something physical that we're used to working with. Okay? Make sense? Okay. Which gets us to our last one, limiting reactant and percent yield. We saw this last Tuesday. For those of you that have checked your email or the announcements on Canvas, you should recognize this question as well, because this is the one that can get you 10 more points on your exam. Okay? What I'm asking to do is take this one question, what is the percent yield? And I want you to break that down into, at minimum, 9 easier questions. Okay? Because there are 9 easier questions that you need to answer to get this overall question, at a minimum. Depending on your level of understanding of the material, you may go through, someone may help you, and you're like, well, I have no idea where you got that equation from. Make an easier question to explain where you got that equation from. You have to scale backwards all the way back to where your understanding is, and then work your way forwards. Okay? I said 9 things, and a lot of people kind of panicked, or I saw some emails about, well, how do I come up with 9 questions to come up with this? I don't know, maybe you look at the slide. 1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like someone counted the lines before they asked the question on what questions need to be answered. This is a good place to start. Okay? If you feel you need some more questions to help you get through it, by all means, go ahead and add those questions. Those are kind of your minimal things. Notice that those are not formatted in the form of a question, or at least some of them aren't. Okay? You may need to actually convert them to a question. And just to be annoying,
What's the minute mark?
you may wonder, where did those questions come from? Look at the slides. The reason I'm putting the PowerPoints together is so that you have access to them. I'm posting them so that you can see them. That information is on the slides. You don't have to take a picture of it, but you're more than welcome to take a picture of it now. Okay, I just wanted to draw attention to that.
I know.
Okay. So if you want a picture of that because you don't want to look up the slides, that's fine. Go ahead and take a minute. Are we good yet? No, one more. Again, it's in the PowerPoint slides. Post it on Canvas. It's there. I fully understand that. I'm right there with you. We good? Okay, let's break the bank. Empirical formulas. Believe it or not, almost everything you've been working with has been in an empirical formula type situation because we've been looking at salts. Okay? So when we look up magnesium chloride, what is the formula for magnesium chloride? So ignore all the questions that are up there. I want the formula for magnesium chloride. Mg Cl2. How did you come up with that? Magnesium is a charge of positive 2, chloride is a charge of -1. It balances, right? Mg2Cl4, does that not balance?
Yeah.
Well, that's interesting, that balances. Why did we not use that as our formula? Because, that's a good answer, I like it. That's not our simplest form. When we're looking at our formulas for ionic compounds, we always go to the reduced ratio. That is always what we report. Okay? That is effectively the empirical formula. That's what it's there for. Okay? There are some cases where we'll start to look at things varying off of that. Okay? So it comes back to the meaning of what that formula gives us. So when we look at the formula for MgCl2, what does it mean? I give you 1 magnesium chloride. What does that equal?
1 magnesium and 2 chloride.
1 magnesium. 1 magnesium chloride, that's a Cl2, gets you
2 chloride.
2 chlorides. That's what the formula gets you. What if I give you 1 gram of magnesium chloride? Convert it to moles. The formula does not tell you mass, it tells you the number of the particles present. Okay, that's what our formula gives us. So when we're looking at our formulas, we have to realize that it is the number of those particles, and that is it. Okay? So let's take a look about, say, the molecular formula. Oh, I must have read the question. I didn't realize I asked magnesium chloride. There we go. Look at that. Let's take a look at the molecular compound benzene. So now we're going to switch things up because it's no longer an ionic compound. Anybody know the structure of benzene? I'm just curious.
Circle.
Pretty close. Whoops. Hexagon. Again, close. There's our structure for the molecular compound benzene. Okay, kind of round on its face at the bottom. Okay. If we were to go through and look at the structure in Gen Chem, you would not see the structure. Why not? How many of you were trained to draw that structure? You weren't. You don't have the rules to draw it. That's fine. How would we draw this or represent this compound in this class? With a formula. Okay, so there's carbons in it, there's hydrogens in it. How many carbons? 6. How many hydrogens? 6. Okay. What is weird with that formula? It's not the simplest form. Really, that should be C1H1. But if I take C1H1 and try and make benzene, is it going to work? No. Molecular compounds follow under a different set of rules because their bonding structure is different. Their bonding structure is different because what type of bond do we have?
Double bond.
No. True, but no.
Hydrogen bond.
Not hydrogen bond. That flips me out. Covalent bonds as opposed to ionic bonds. Okay? Covalent bond means nomenclature rules change. What does that mean about formulas? It means our formula rules change. Okay? So we need to represent or see the comparisons between these and come up with some way to name and identify them. The empirical formula is by definition the fully reduced form. So when we look at benzene, C1H1 is the empirical. I have no idea how to spell empirical. Empirical formula. I cheated and looked at the screen. For those of you being impressed with my spelling. Okay. The C6H6 is the molecular formula. Okay. Why would we use one over the other? Okay. Really, the empirical formula coming from an organic chemist is virtually useless. The only reason we use the empirical formula is we have no clue what we're looking at and we ran an experiment and we're trying to determine what the molecular formula is. We want the molecular formula. Okay? So the question becomes is how do we determine the empirical formula and then by correlation get it back to the molecular formula? That involves a whole bunch of extra calculations. Okay? So here are all of our steps. I know it's a lot of steps. So just breathe, take a minute, read over it. What was that?
So where are your condensed rules?
These are the condensed rules. Come on, you compare this back to Lewis structures. This may look like a lot more rules than Lewis structures. Lewis structures had a size like 12 font. This is something like a size 24. Okay? There's only 5 rules here, guys. Okay? And a lot of this comes from understanding what our formulas give us. The molecular one's a bit nasty. The empirical one just comes from understanding what the formula means. Okay? So we will pop these slides back up again, or this slide will show up again after we look at a calculation. Ooh, please connect. Good. So our empirical is our fully reduced whole number ratio of each of the elements. Okay? So our subscripts represent the number of atoms within that compound or the number of moles. So let's take a look at an unknown compound. Somehow or another, we take this unknown compound, we spit it into a machine, the machine spits back out this answer, or this information. There are 0.726 moles of radium in this sample, and there are 12.3 grams of oxygen atoms. That's an of, not an or. What is the empirical formula? So what is our general form for our empirical formula? What's the first element? Radium, which has what symbol? Okay, what's the next element? Oxygen. Rao. It's a fun one. Okay. How many radiums are present in that formula? 0.726 moles. Well, that's the number, right? What did our empirical or our formula give us? The number. Okay, so I can put in 0.726 for radium. That's perfectly valid. Why not? That's the number of radium in that sample. This should be a whole number. So that's kind of ugly. We want to get that into a whole number. Okay, to get that into a whole number, I have to know the ratio of radium to oxygen. Okay, so how much oxygen is present? 12.3 grams. Remember, our formula tells us the number of things present, not the mass. Which means, is our 12.3 grams allowed to even show up in our formula? No. What do we have to do to the 12.3 first? Convert it to grams. Moles. Someone say convert it to grams?
You said it yourself.
I don't believe you. I think somebody said it to trick me. 12.3 grams of oxygen. Should I be looking at oxygen as O2 or oxygen as O? Why O? It says oxygen atoms specifically in the question. That's how we know. Okay. What did I want for my answer? Moles of oxygen, of just O. What is the relationship between the grams of oxygen and the moles of oxygen? 16 grams is 1 mole of oxygen, and you know that because? The periodic table. Okay, since you got a calculator, what did that give you? 768.
75. 4.
No, I'm stopping there. That's too much. Moles of O, right? So we can now take that number and drop that into our formula. And now our formula becomes crystal clear, right? Okay, that's pretty ugly looking. We want a whole number ratio, so what should we do? Pick whichever one is the smallest and divide both numbers by that. Which one's the smallest? What is 0.726 divided by 0.726? What is 0.76875 divided by 0.726?
1.06.
Okay. 1.06, can I really have 1.06 of an atom? No, really, what are we saying? 1 to 2? That's a bit of a rounding up.
100 to 106.
Our empirical formula is RAO, 1 to 1. That's it. Okay. If we go back to our, well, actually, before I go back to the rules, we now have our empirical formula. That's our answer. Questions about what's up there?
So because O is not like significantly bigger enough, is that why it's just only one?
We look at that number and we're saying, how is it close? What is it closest to in this case? When you're doing your empirical formulas, your numbers will come out at very close to whole numbers-ish. For the sake of this class, they will always come out darn close to whole numbers. If you run a question on this in the textbook, it is possible you will see another variation. It won't come out close to 1 or 2, but it'll come out close to 1.5. What happens if you get 1.5? 1.5, there's nothing to round. It's right in the middle.
Multiply it by something.
Multiply it by something. 1.5 comes out as 3 over 2. Multiply everything by 2. Scale everything up by a factor of 2. Now everything's a whole number. Okay. The other value it'll come out close to 1.33. Multiply everything by 3 and it scales up. Okay? So for the sake of this class, you will always come out almost on the button, okay, for whole numbers. Okay. The textbook may throw a curve at you where they aren't coming out to on the button. Everything I'll show you is right on spot. Okay. Questions about what's up there?
Why would, I mean, for obvious reasons, I mean, it gives us numbers there, but why wouldn't you just look at the charges because they match up there?
So remember why we ended up looking at this. So you're right. If we look at the charges, it would balance out here. And that's because this is an ionic compound. So really, I picked a crappy question because you used your chemical knowledge to say, hey, dude, the charges balance out. Okay, I screwed up. What I should have given you was something like benzene. What's the issue between benzene and radium oxide? Benzene is covalent versus ionic. Okay? So the other case where this can show up is for ionic compounds where we don't know the charge on the metal. Radium is a horrible example. I need to change it because people keep asking, why don't you just do that? You're right. Yes, you can do that. I screwed up. Okay? If we go back and look at how we converted our empirical formula, our very first step was to convert the units into moles for each element. One of them was already in moles. The other one was in grams. What did we do to the one in grams? Change the moles using molar mass. Notice part B, it says percent composition. Did you see anything about percent composition? No. So what should you do? Ignore that rule. That's nice. Step 2, divide all of your mole amounts by the smallest mole. That's exactly what we did. And we end up with our empirical formula with our whole number ratios. Make sense? What happens if instead of giving grams, you were given percent composition? What does percent mean? Out of 100. Okay, so if I tell you it was 12% carbon, what does that mean? 12 grams out of a 100-gram sample was carbon. You now have a gram amount, 12. Convert that 12 grams of carbon into moles of carbon. Do that for every other element out of that 100-gram sample. So we assume a 100-gram sample because that makes our calculations easier. Okay? Molecular formula becomes a little bit challenging, a little bit more challenging. You will determine the molar mass of your empirical formula, okay? And then you will divide the molecular molar mass. That number has to be given to you by the empirical molar mass. Okay? Remember, your empirical ratio is the smallest reduced ratio. Okay? It can scale up, but it will only scale up by whole number integers. So if I divide those two values, what will I end up with? A whole number integer. I can multiply everything in the empirical formula by that whole number, okay? And I can scale up. Okay? So when it says by number from 2, that's what step 2 is saying. Okay, so let's take a look at this one, because I think we've got it here. Yep. An unknown sample was found to be composed of 24 grams of carbon, 2 grams of hydrogen by elemental analysis. What is the compound's empirical formula? Should this be a quiz? I mean, it's just more opportunity to get points. Maximize your quiz points.
All in. Gung ho. Rock and roll.
Okay. Sorry, for those of you who still had hands. Your empirical formula should have come out to be CH. A couple people came out with C2H2 because that's what the question takes you to. Okay? But you have to realize your empirical formula is the reduced ratio. Can we take C2H2 to smaller values?
Yes.
Yes. So it has to become CH, C1H1. Okay? To determine your molecular formula, we have to see how many times C1H1 fits into the mass of our molecular compound. Okay, well, what is the mass of C1H1? 13 grams per mole. A couple people were saying, taking the moles from the previous question. There were 2 moles of carbon and 2 moles of hydrogen. Okay? That came from a sample. Okay? We don't know how many of the molecule was in that sample. So you can't use that value. You're using the molar mass of your empirical formula. In this case, there's 1 carbon with a mass of 12. And there's a mass of 1 hydrogen, which is a mass of 1. 12 and 1, 13. How many times does that 13 mass unit fit into 78?
6.
Said another way, take 78 and divide by 13. What do you get? 6. So that 13 unit, okay, our empirical formula, needs to be repeated 6 times to get me to a molar mass of 78. So my C1H1 becomes C6H6, also known as benzene. Look at that. Somebody was thinking about repeating themselves. Okay.
So is that what you do with whatever you find out, you just replace your subscripts?
Yep. So careful. It's not replace the subscripts, it's multiply the subscripts.
Oh, okay.
Because if it was C1H2, if you scale up by 6, it becomes C6H12. Okay, because you're fitting that whole unit in 6 times. Okay, so there's our summary again for coming up with those steps. I find this kind of calculation a bit obnoxious and tedious because we have much better methods for determining a lot of this information. Okay. In the future, you probably won't see it in this class. There's our percent value. If you see a percent, assume 100 grams. You now have the mass of each of those species. Turn it into moles. You now have your empirical formula and run away with it. Okay. Yeah, so that was it. Questions about that? Okay. I'm going to start. I know we only have a couple minutes here, but I'm going to start into this next section because you will find there are certain things throughout the semester that I started yelling and screaming and getting excited about, right? This happens to be one of them. Okay? Forces and the implications. Right? Massively, massively important. Right? You may all get bored with me talking about it, but it's all going to come back to some kind of basic concepts that you should be understanding within chemistry. All of chemistry takes 2 atoms and we interact them. Okay? We want to then decide how those interactions play out in the larger scheme of things. Do we make a new compound? Do they repel? Do they explode? In all cases, it's just taking those 2 atoms, putting them next to each other. What happens? Okay? So first thing we have to consider is what makes an atom. So, well, what makes an atom? Protons. Neutrons, both of which are in the nucleus. I agree with you. And electrons. we're looking at how those three particles can interact with each other to generate a larger atom. Once we have that larger atom, we then look at how that larger atom interacts with a second atom or a second arrangement of protons, neutrons, and electrons. Okay? And we evaluate those types of interactions. Okay? That's it. If we're now going to take these two atoms and bring them close to each other, what's the first part that they're going to see?
Electrons.
The electrons. So how those electrons interact between those two atoms is what we're going to talk about in this next unit. It's no longer mathematic. It's thinking about how interactions occur and how we can start to predict and use this information. Okay? Super important. Hits close to home. It'll come back to hydrogen bonding, okay? Which is not a bond. Okay? We'll pick up there on Thursday.